All right, here we are with chapter 18, talking about how atoms bond and how do molecules attract to each other. Okay, first of all, we're going to talk about the electron dot structure, and this has to do with the valence electrons, which is what we talked about before. Valence electrons are the electrons on the outside layer. So, for example, if I have hydrogen, the valence electrons have one proton, and I have one electron. So this would be my valence electron. On the other hand, say I have, say, sodium, which is element number 11. All right, sodium has 11 protons, and it has about, I believe it's 12 neutrons, and it has 2 electrons on the first level. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Excuse me, that's not right. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's take off a couple of those. I got a little carried away there. All right, 1, 2, 3, 4, 5, 6, 7, 8. That makes a total of 10. Now, that means on the outside layer, it has 1 electron. Okay, so if we're going to draw the electron dot structure, we take the symbol of the element, okay, hydrogen, and we would put 1 dot for each electron that it has in its outside level, or valence electrons. Okay, so both sodium and hydrogen would just have 1. Okay, now if you remember, we said this outside layer can only have up to 8. Okay, and so let's just say, let's take one like, say, fluorine, okay, which is element number 9. Okay, fluorine would have 9 protons, because that's the atomic number, which tells us the number of protons, and it would have, I believe, about, let's see how many electrons. 18 with us, but it have 10 neutrons. Okay, so it have 10 neutrons in the middle. All right, neutrons plus or minus. Okay, and then it would have 2 electrons on the first level, and have 1, 2, 3, 4, 5, 6, 7 on the second level for a total of 9 electrons, which makes a neutral atom. Now, to do fluorine, okay, it actually has 7 on the outside layer. Okay, so here's what we do: is there are 4 pairs possible on the outside layer. So what they first do, the electrons try to get as far from each other as they can. So we have 1 pair that would go up here, 1 on the side, 1 down here, and 1 over here. And so the first 4 electrons would spread themselves out, and they would go to each of these 4 little subcompartments before they would double up. Now, since we have more than 4, okay, once you get to the 5th electron, you're going to have to start doubling up. And it doesn't really matter which one you double up with. That would be a total of 5, and then 6, and then 7, which is all we have on the outside layer, which leaves us with 1 missing one over here on the end. Okay, and so that would be the electron dot diagram structure for some of the Lewis dot structure for fluorine. Okay, it would have 7 electrons on its outside layer. Okay, oxygen has 6. So it would have 1, 2, 3, 4, and then fill up 2 more. It would have 2 that are paired electrons that are basically full, and there would be 2 pairs that are not full. Okay, and so the main thing to remember is you just put dots on the 4 sides of the symbol, and once you have dot on all 4 sides, if you need more dots, then it'll start to double up. But for example, say magnesium has 2. You would never put 2 right there on the same side. Okay, you would always put 1 on that side and 1 over here. Okay, or it doesn't really matter which 2 sides you put them on, but there would be 2 dots, and they would be separate until they get to 4, and they have to pair up. Kind of think about it, if it's you and your little brother or sister sharing a bedroom, you would spread people out in their own bedroom until they had to pair up and share a bedroom, which me and my brother had to do growing up. So that's the same thing here. They don't want to pair. Now, these pair valences, all right, or valence electrons, for example, a pair right here is non-bonding. Okay, so these paired electrons, or electron pairs, you may hear it called either way, paired electrons are non-bonding. In other words, they are stable, they're happy the way they are, and when you try to join it to another atom, they are not going to participate in that. However, these that are unpaired, such as the one over here in fluorine, these two over here on oxygen, these two on magnesium, this one on sodium and hydrogen and so forth, those are unpaired electrons or unpaired valence electrons, okay? And these unpaired valence electrons are the ones that will do the bonding, and they're responsible for how these electrons will bond with each other, okay? And so basically, these atoms, when we took a look at their electron Lewis dot structure or the electron dot structure, these are talking about neutral atoms, okay? In order to have 9 protons, it has to have 9 electrons to be neutral, and so it does. And same thing with sodium has 11 protons, 11 electrons if it's neutral, and hydrogen has 1 proton, 1 electron, which makes it neutral. The problem is if you have neutral atoms, you can't stick them together. You can't make things out of them, okay? And so we would just have clumps of elements or a bunch of elements floating around but not make anything like people or animals or dogs or cats or anything else you want to make. All of those have to have charges in order to stick atoms together, okay? And when they become charges or have charges, okay, we call them ions. All right, so you have neutral atoms that have no charge, and you have ions, okay? And so we look at the periodic table, and we're going to take out the middle section for right now, not worry about it. But here's the first 2 columns over here, the alkali earth metals, the alkali metals, and then we have over here, we have a little stair step would be coming through here, and we would have a little stair step that would drive through there. Try that again. Like so. Okay, that would be our little stair step with the metals here, non-metals over there, metaloids touching the stair step. Okay, and we have all the electron dots. You notice over here, these all in this column have 1, all in this one have 2, all in this one have 3, all in this one have 4, and then 5, and then 6, and then 7. And then finally, in the last one, the helium has 2. The rest of these all have 8 in their outside layer. Okay? And so when they become charges, okay, there's basically 2 rules. We have the positive ones over here. They do not have very many electrons on there. Okay? And they want their outside layer to be full. To be full, okay, this layer, for example, for say potassium here, it has 1. Okay, to fill that layer up, it would need to get 7 more. Okay, or it could get rid of that, and then the ones inside of that, those layers would be full. Okay, and so basically, what most metals are going to do, they're going to get rid of their electrons, which gives them a positive charge. And so we put a +1 charge, and so we say that they will become cations. Cations are just ions, or positive ions, ions with a positive charge, okay? But if you look at the non-metals, they all have 4 or more for the most part in theirs, okay? And since they have 4 or more, it's easy for them just to fill up the layer they have. And so fluorine would gain 1 more electron, which would make it -1. These would gain 2, which makes them -2. These would gain 3, which makes them -3. Now, right in the middle, you have 4. Well, they could either lose 4 or they could gain 4 to fill it up. So they tend to be plus or minus 4. They could go either way. And the inert gases or noble gases over here have 8 in their outside layer. And so they're happy. They like the way there is. And their charge is basically 0. They can be forced with a lot of pressure and so forth. But generally, your metals are going to become cations. Your nonmetals, since they all have negative charges, are going to be called anions. Okay, which are just negative ions. If you think about this, A negative, AN ions, A negative ion is an anion. Cations are a positive ion. Or you think I positively hate cats, I positively adore cats, whatever, and that the cations are positive, anions are negative. All right. So when these atoms join together, it would be very easy, for example, say sodium has 1 valence electron. And you may remember, we were talking about electricity and stuff last semester if you were here. Metals tend to just let their electrons go. They're not real careful about them. Okay, and so what happens is, if you take fluorine, who likes to hang on to electrons and would like to gain, it wants to fill up its outside layer. Sodium wants to get rid of it. So normally what happens is this little electron would come over here, and you end up with sodium, which now it lost a negative, so instead of being neutral, now it's +1. And you have fluorine, which gained an extra electron. Okay, so now it has a -1 charge. Well, since this one's +1, this was -1, they stay attached to each other. They attach to each other, okay, because of the opposite charges. Okay, and since they're opposite charges, we call this an ionic bond. Okay, ionic because they're ions. One has a positive charge, one has a negative charge, and that holds them together. Okay, and so they're attracted to each other. It holds them together and makes a compound called sodium fluoride, which is a very common compound in toothpaste. If this was chlorine instead of fluorine, you would have sodium chloride, which is table salt. But the same thing, it's an ionic bond. And in this case, the metals are going to lose electrons. Okay, and the nonmetals are going to gain electrons. Okay, and so, and when they do this, they both have opposite charges, and therefore they're attracted to each other, and they join together. And that's an ionic compound. Many minerals, salt, rock salt, is like this. Very crystals and stuff. Calcite, which makes up gypsum. Pyrite with fool's gold, comes in little goldish colored things. Pyrite as iron and sulfur. Halite, which is rock salt, basically. All these things. And so in an ionic compound, you have to have the same number of positive and negative charges. Okay. In this case, sodium had 1. But let's say we wanted to stick it with fluorine. We still got fluorine here, which needs 1 here. All right. But let's say we have a magnesium, and magnesium has 2 electrons that it needs to give away. If it gives one of them away, let's just say this one, okay, and it gives it away, and so it comes over here. This fluorine is happy, and it has a -1 charge. But magnesium is not happy. It still has this electron it wants to get rid of. So in order for fluorine to react with it, it actually takes 2 of the fluorines, and now this electron can go over here. Okay? And so in order for magnesium to react, it has to get rid of both electrons, which gives it a +2 charge, and now you have 2 fluorines. Each one's a -1 charge for a total of -2. And so magnesium, and then this magnesium would be attracted to these, and they would stick together to make magnesium fluoride. But magnesium fluoride, if we're going to write the formula for it, would be MgF2, because there are, in fact, 2 fluorines for every magnesium, because each fluorine can only take 1 of those electrons from the magnesium, and it takes 2 of them to get rid of all the magnesium's electrons, and so that it will be happy, okay, because its outside layer is empty. It's what it needs to do to be happy. And to make it balanced and even, we have to have magnesium with a +2 charge and the 2 fluorines with -1 apiece, making a -2 charge. And so the whole compound, the ionic compound, is balanced because you have the same number of positive and negative charges. All right. That's an ionic bond. Let's look at a little different bond. This is called a metallic bond. Okay, a lot of metals, you have a big chunk of metal, and it's made out of a bunch of metal atoms that are all hooked together. Okay, in a metallic bond, things are a little different. You have the nucleus with its positive charges, and they kind of just let all their electrons between them just kind of go back and forth. And so we say that the ions form a lattice or a framework, and the electrons just kind of move around in between that. Okay, and because these electrons move very freely, they very easily carry heat or electricity, both of which cause electrons to move from one place to another. And so metallic bonds allow for this movement of electrons, and that's why metals are such good conductors of heat and electricity. All right, and let's stop right there. We'll come back to that and finish up on some of our other types of bonds.